In this video, we're going to be discussing partial fraction decomposition. Sounds like a lot. It's really not too bad. The big idea comes down to looking at an expression like this. Now, normally when we would have an expression like this, we would combine these guys. We would put in the missing factors. So here we'd be missing the factor x minus 1, which goes in the numerator as well. And on the other side here, we have x plus 5 that's missing. And so we'd put all of this stuff together over our big common denominator that is made up of the factors x plus 5 and x minus 1. Now the numerator is stuff that we can just kind of work out here off to the side, so that would be 2 times x minus 1 plus 3 times x plus 5. And so we just work this out, 2x minus 2 plus 3x plus 15, and altogether this is 5x plus 13. And that is how we would end up with our expression. So it's one thing to combine to get to that. It's another thing entirely to be given this and say, where did it come from? What fractions did we add to get there? And that's what partial fraction decomposition is all about. So let's take a look at this example right here. X minus 1 over x squared plus 8x plus 15. Now, if you look at this denominator, it's made up of the factors x plus 3 times x plus 5. So we'd be thinking that this guy surely comes from having, two smaller parts, where one of these guys is the denominator x plus 3 and the other one has the denominator x plus 5. So how do we figure this out? Well, you can see a lot of different cases here in this series of videos. So as long as we don't have any repeated factors, you just put them there one time each for their own fraction. If the denominator is a linear factor, then in the numerator, we're going to put these unknowns here. So let's say a, and we're going to say b over here. If we had a third factor, of course, you would say c and then d and so on. And somehow, this is supposed to be equal. Now, it all comes down to understanding about how you would clear fractions from rational equations from before. So the common denominator would have to include all of these factors, x plus 3 and x plus 5. So if I put in those missing factors over here, you can basically wipe out all of those denominators because they're all the same. And that would leave us with the expression, or the equation, x minus 1 equals a times x plus 5 plus b times x plus 3. Now, there are two ways of going about solving this. There's kind of an easy way, and then there's a shorter way. So make sure that, actually, those are both the same thing. There's an easy way and a hard way. That's what I meant to say. Whatever. So the easy way is to kind of pick and choose values of x to make one of these unknowns go away. For example, if I look here, there's a critical value that would make that 0, and that's when x equals negative 5. So let's check this out. What happens when x equals negative 5? Well, that means I'd be plugging in negative 5 into all the places where I see x. So on the left side of the equation, we'd have negative 6. On the right side, by plugging in a negative 5 right here, this whole guy goes to 0. Now I don't have to worry about him. I would then plug in negative 5 here, and that gives me negative 2 times b. And very quickly, we can see that, well, if I solve this nice linear equation, that means the b value is equal to 3. Cool. Well, let's do it where we can cancel out or get rid of the b. So the other critical value is going to be when x equals negative 3. So let's plug in negative 3 and see what happens. Whoops. Getting rid of stuff I did not mean to get rid of. Oh, and I didn't get rid of stuff I meant to get rid of. All right. So now if I plug in negative 3 for all of these x's here, well, we can see here that negative 3 plus 3 is going to become 0, so that whole guy is gone. On the left side, negative 3 minus 1 is negative 4. And when I plug in negative 3 here, I end up with a positive 2, so 2 times a, which means a equals negative 2. So we will use these guys right here that we found for a and b, and that tells us how to break down this fraction. So that means that my fraction from up above breaks down as, let's make sure I don't miss this, so it's a, so it's going to be negative 2 over x plus 3 plus my b value, 3 over x plus 5. This is my partial fraction decomposition. Now what you can do, if you don't believe me, is that you can take this expression and combine it into a single fraction, and you'll see we get exactly what we were supposed to have, what we started with. So this is the easy way. Now there's a more difficult way here. I want to make sure you see this because sometimes we do need to apply this. Let me take this equation and rewrite this. So that's x minus 1. On the right side, let's go ahead and distribute. So we end up with a times x plus 5 times a plus b times x plus 3b. From here, we can form a system of equations. Let me highlight all of the x terms right here. So we can write a system that says when I take the coefficients here, a and b, that should equal the coefficient for x, which is 1. So ax plus bx is supposed to equal x. In other words, a plus b equals 1. And then we look at the equation we can form from the constants, negative 1, 5a, and 3b. So that means 5a plus 3b equals negative 1. So we have a system of equations, 2 unknowns, and if you solve that for a and b, you're going to find out that you still get 3 and negative 2. Now, writing it as a system should always work, right? Sometimes there's a little bit more work to do whenever we're just kind of plugging in numbers, but you've got to be very smart about the numbers that you choose to plug in. Here I was choosing those critical values, those values that would make those factors equal 0. And since a and b were connected to different factors, I was able to eliminate them one at a time, and I could focus on just a or focus on just b. So let's take a quick little break and see how that can be applied in the next example.